Let's look at another one. Man walks along a straight path at a speed of 4 feet per second. A searchlight is located on the ground 20 feet from the path and is kept focused on the man. At what rate is the searchlight rotating when the man is 15 feet from the point on the path closest to the searchlight? Sometimes the hardest part is figuring out what this situation looks like. You'll get better with practice. We've got a straight path, so let's draw that. Usually the ground is lower in our picture, so there's the path. Man's walking along it, so there, simple picture of our man. Speed of 4 feet per second. We'll get back to that. The searchlight is located on the ground 20 feet from the path and kept focus on the man. So it doesn't sound like there's anything in our picture that's like in the sky. So this is a flat ground that we're going to draw. The searchlight is away from the path. Let's say it's up here. There's our light. Okay. And it is located on the ground 20 feet from the path. Anytime we're measuring from a point to a line, it is straight there at a right angle. Now it's kept focused on the man, so the light is only beaming in this direction. It's kept focus on the man. That's the path of the light. At what rate is the searchlight rotating? Because it's focused on the man here, not looking anywhere else, and it stays focused on the man. So there's the rotation factor in there. So this is an angle that's changing. Let's call that angle theta. At what rate is the searchlight rotating? So that's an angle that's changing. An angle is changing when I see rotating, and that's a rate, so we know that means derivative. When the man is 15 feet from the point on the path closest to the searchlight. Here's the point on the path closest to the searchlight. So we're measuring his distance here as he's walking. Now it doesn't say if he's walking away or towards that point, but it is measuring that distance. I'm going to call that distance x because it's a horizontal distance. When the man is 15 feet from that point, so if we're trying to list our find, when and given, I want to jot down that piece of information. So when x equals 15 feet, when this distance is 15 feet. What else can we put in our find when given? A man walks along the straight path at that speed. Well, speed is a rate. That's a rate. And it's walking along that path. So it's the rate that this is changing. So that's dx dt 4 feet per second. It's how fast this length is changing. And more information coming. A searchlight is located 20 feet from the path. So this length right here, 20 feet. It's always here. It stays here. It's not moving. And the path stays here. It's not moving. So this is constant. And if it's constant, we mark it in our picture with a number. I wrote down the 15 feet. At what rate is the searchlight rotating? That's the question. What rate? So d theta, the change in the angle. At what rate is that angle changing when the man's 15 feet from that point? Now notice this is another triangle problem. However, it's an angle that we're measuring this time and not the sides of the triangle. So instead of Pythagorean theorem, we want to think of an equation that relates angles to sides. That's going to be using triangle trigonometry. So from this angle, we have sides that are opposite and adjacent. That's a tangent equation. So we're going to write the tangent of theta equals x is opposite, 20 is adjacent, and it's opposite over adjacent. There's our equation. Now we can take the derivative. The derivative with respect to t of the tangent of theta, and the derivative with respect to t of, let's call this 1/20th x instead of x over 20. Derivative of tangent is secant squared theta, but it's chain rule because the variables don't match. Over here, the derivative is just the constant multiple, but the variable doesn't match, so times dx dt. Now we need to plug in what we have, our when and our given, to get our find d theta dt. So this will be the only guy that's left blank. Now we don't know theta, so how am I going to find secant squared theta? Let's use our triangle to help us do that. If Well, let's plug in what we know already here. We know this is 4, so secant squared of theta is the only part I don't know because this part I'm trying to find. That's the part that I don't know. So let's go back to our picture, and we need to figure out secant squared of theta, or secant of theta squared, what's that, so that we can plug it in over here. Let's start by identifying what is the secant of theta. Secant of theta is 1 over the cosine of theta. And if cosine of theta is adjacent over hypotenuse, secant of theta is that reciprocal. So hypotenuse over adjacent. Well, in our picture, I don't have the sides labeled, but remember, after I take the derivative, I can plug in my when. My when is x is 15. So when x is 15, and that side is 20, here's our triple 3, 4, 5 multiplied by 5 times 5 makes 15, 20, 25. So 15, 20, our hypotenuse is 25. So hypotenuse over adjacent gives us 25 over 20. Or to simplify that, the secant of theta is 5 over 4. Then we can figure out secant squared of theta by squaring both sides, 25 over 16. So secant squared of theta is 25 over 16. So now I can get d theta dt by itself. 25 over 16 d theta dt equals 120 times 4, or 4/20ths, or 1/5 d theta dt multiplying by the reciprocal. 1/5 times 16 over 25 looks like 16 over 125. Now, we're always measuring angles in radians, so radians, and the time is in seconds, so radians per second. Remember, given words in the question, we give words in the answer. So we can say, when the man is 15 feet from the point on the path closest to the searchlight, the searchlight rotates at a rate of 16 over 125 radians per second. We're going to do just one more. I know your notes have another one, but it's identical to number 4, slightly different numbers. So we're just going to do one more, just number 4. An inverted cone. Inverted cone means it is resting on its vertex. Has a height of 9 centimeters and a diameter of 6 centimeters. It's leaking water at a rate of 1 cubic centimeter per minute. Find the rate at which the water level is dropping when the height is 3 centimeters. So we have a cone that's holding water, and this cone is always 9 centimeters tall and 6 centimeters wide. The diameter 6 centimeters. It's talking about its leaking rate. It's leaking water at a rate of 1 cubic centimeter per minute. How do I know what that's measuring? Cubic units measure volume. Rate derivative. So this is dV dt that they're giving me right here. Remember, cubic units is volume. It tells me it's volume. Find the rate at which the water level is dropping when the height is 3 centimeters. So the cone always is the same, but the water that's inside the cone, that's a different story. The water inside the cone is another cone of water that has a height that's changing. Let's call it h for height. The height of the cone of water is changing, and perhaps this helps to see the water that's in there. The radius of that cone is also changing, and I'm using radius because when we describe the volume, the equation is given in terms of radius and height. Our equation for volume, our formula for volume of a cone is V equals 1/3 pi r squared h. So I'm going to go back up here, and instead of writing 6 centimeters for the diameter of the cone, I'm going to show 3 centimeters for the radius of the cone. Let's list our find when given so we keep track of what we want to find, when is the moment in time, and what's other information. Once we list these, we don't have to go back to our words. An inverted cone has a height of 9 centimeters, we drew it. Diameter 6 centimeters, we drew it. Leaking water at this rate, that's given information, dV dt. Now it's leaking, which means the water is going down, so it's a negative rate, -1 cubic centimeters per minute. Find the rate at which the water level is dropping. That's the height, the rate that the height is changing. So find dH dt when, here's my when, the height is 3 centimeters. So when the height is 3 centimeters. Now that I have my find when given, I have my equation. Usually we just go straight into the derivative of that equation. However, note that there are two variables over here, a product of two variables. I would have to use the product rule. I would get an r, a dr dt, a dH dt. I only have information about h. So I don't want to leave this r in the equation. We're going to do something that helps us get rid of multiple variables. We're going to find a way to relate r to h. Now notice in this picture we have a little cone, we have a large cone. They are similar cones. Similar cones mean we can make a proportion. So how is r related to h? R to h is 3 to 9. R to h is 3 to 9. That's our equation that relates r to h. These are similar, so we're making a proportion. We could have done it as r over 3 equals h over 9, as long as we're staying consistent. So r over h equals 1/3. Get rid of the h from this side, and r equals 1/3 h. Take that, plug it into the r, so everything is just in terms of h. So v equals 1/3 pi. R is h over 3 squared h. Simplify this. Pi over 3, h squared over 9 times h, or pi over 27 h cubed. Much simpler, easier to take the derivative. dV dt equals pi over 27. Derivative power rule, 3h squared dH dt. Plug in what we know. dV dt is -1, pi over 27. 3h is 3 squared. dH dt I want to find. Looks like I'm going to get 27 over 27. Divide by the pi, and dH dt is -1 over pi. H is measured in centimeters. T is measured in minutes, so centimeters per minute. Now you can practice writing your answer in words. So when the height is 3 centimeters, the water level drops at a rate of, now that's negative, but when I say drops, that's negative wording right there. So 1 over pi centimeters per minute. I don't say drops at negative. That's a double negative. So drops at this positive rate.